let's take a brief look into the architecture. Here I've shown a couple of camera streams, the fisheye camera, which is a front-facing wide-angle camera, and the left pillar camera, which is a left side-facing camera, but it does take all the cameras as input. We first normalize to remove any vehicle-specific configuration, such as intrinsic calibration or distortion or things like those. Once we have normalized these images are then fed into state-of-the-art image backbone architectures. So here, for example, we use regnets and BiFPNs to extract the image features. But this can be swapped with the state-of-the-art architecture from even, for example, CVPR 2022. These backbones now produce features, the high-dimensional features in the image space. But we want the occupancy to be in 3D, right? How do we get this? We use query-based attention to produce these 3D occupancy features. This is, in fact, similar to how a paper of the same name, Occupancy Networks, came out a few years ago, which again queries 3D points for whether that 3D point is occupied or not. So here it's of similar nature, where we are taking 3D positional encoding, then mapping that into fixed queries. These fixed queries then attend over every image space feature. We also have positional embedding in the image space. So now these 3D queries attend to image space queries of all the image streams and then produce 3D occupancy features. Since these are high-dimensional features, it's hard to do this directly at every point in space. So what we do is produce these high-dimensional features at a lower resolution, and then use typical upsample techniques like decons or what have you to produce denser, high-resolution occupancy. An interesting fact is that when we started out this project, we initially were only targeting to do static objects, such as walls or trees, because we have lots of different neural networks running in the car that deal with different kinds of obstacles. So we had and continue to have a network that primarily handles moving objects such as vehicles, pedestrians, bikers, etc. And these networks also produce the full kinematics of the vehicle, such as depth, velocity, acceleration, jerk, etc. So we have this moving object network, and we thought, okay, we do not need to deal with moving objects here. We just need to deal with static objects such as trees, walls, etc. It turns out that having an explicitly defined ontology tree can be pretty tricky to produce. So here in this example, this is from our own internal testing as well, where there's a pickup truck that looks like a fence. When the vehicle was moving on the highway, we obviously knew it was a moving object and it was produced as a truck. But then when the vehicle stopped for multiple minutes at a traffic light, we thought, okay, it does look like a fence. Maybe it's not a moving object. And the moving object network decided that it's not a moving object. But obviously, we do not want to drive into this vehicle. We want to control for it and drive around it or slow down appropriately. This can get even trickier with pedestrians. On the left here are false pedestrians, where these can be like statues or mannequins dressed up like real people, but those are by definition false pedestrians. And on the right side, you can see some true pedestrians, like a person in this Halloween costume standing on the side, or this crouched up pedestrian who could look like a pile of trash from far away because of how their posture is right now. This is obviously an impossible fight to fight, and we do not want to fight this fight. We just want to avoid the obstacles and hit neither moving nor stationary obstacles or anything for that matter. So our solution to this problem is to produce both moving and static obstacles in the same framework. This way, things cannot slip through the cracks in between moving and stationary. In fact, what we realized was that there is no such thing as stationary obstacles. Any object, when enough force is applied, will move, and hence is a moving object. So this distinction doesn't even make sense fundamentally. Anyway, to deal with this problem, we have introduced dynamic objects also in the same framework. So now the occupancy networks produce everything that's occupied in the scene. It doesn't distinguish between these things in the occupancy. We can have additional semantic classes that can help with the control strategy later on. But in terms of pure occupancy, it does not distinguish between what is the reason something is occupied. It gives instantaneous occupancy. But that is not sufficient to drive, because if you just have instantaneous occupancy, say you're following a vehicle on the highway, we don't want to assume that the occupied voxels are at 0 velocity and then just slow down, because you want to slow down to avoid these stationary obstacles. What we instead want to know is future occupancy. At different times, how would the occupancy change? This allows us to know that the vehicle in front of us will move away by the time the ego vehicle reaches that location. Hence, we predict, in addition to occupancy, we also predict occupancy flow. This flow can just be the first derivative of the occupancy over time, or can also be high derivatives that can give more precise control. And in order to produce this occupancy flow, we take in multiple time steps as input. So we take all the different occupancy features from some buffer of time, align all of them into a single coordinate frame, use the same upsample techniques to produce both of the occupancy and the occupancy flow. And this provides robust protection against all kinds of obstacles. Here you can see some examples of this combined occupancy plus occupancy flow. The colors of the vehicles represent the direction of the velocity vectors. Here, red means the vehicles are moving along our path, and green means they're moving opposite of our path. You can even see that there's a trash bin that actually flies out in front of the car. We also get that. Here's another example of a strange looking vehicle that's crossing our path. Our regular motion moving object network did not know the type of this object, didn't know it was a sedan or a SUV, etc. But for the purposes of control, it does not actually matter. And this occupancy network provides this nice protection against these kinds of classification dilemmas from the network. Regardless of what's causing the obstacles, it will say that this volume of space is occupied and it's moving at this rate. These kinds of vehicles can also have strange protrusions that are hard to model using traditional techniques. Typically, people reach for either cuboids or other polygonal shapes to represent moving objects, because for the most part that is sufficient. But then the object can have arbitrary extrusion like so. And with this approach of occupancy, we get all of these protrusions for free without requiring complicated mesh-like topologies. And finally, we can also use this geometric information to reason about occlusion. When the vehicle is making a protected or an unprotected turn, it needs to reason about both the things that it sees, like vehicles that are currently visible, but also vehicles that it cannot or might not see. Here, for example, this vehicle is making an unprotected right turn. There is a crossing road in front of it, and there can be potential vehicles that are occluded by the trees and the signpost on the left side here. So the car knows that it cannot see the road from these occlusions, and it also knows why it cannot see them. It knows that it's occluded by either a tree or by a different moving object. And there are different control policies that the car can come up with to deal with this and remove this occlusion. So for example, for a stationary object, it can crawl forward a few centimeters or meters before encroaching into the crossing road and check for when it becomes visible. And since we have the full 3D obstacles, we can also reason about at what speed would we hit this, at what distance would we hit this, and then have very nice, smooth control to creep up and look for these occluded objects. So this occupancy networks helps in lots of different ways to help improve the control stack. Zooming out a bit, the team thinks of occupancy networks as an extension to neural radiance fields. As many of you know, neural radiance fields have taken over computer vision research to a large extent over the last couple of years. There's a lot of interesting work happening in this field. And this bodes really well for us because in our mind, this is the same approach. Neural radiance fields try to reconstruct the scene from multi-view images, essentially. But the way typically it's done is it is reconstructing the scene on a single scene or a single set of location, images from a single set of single location. So to start out with, we can take on any trip from the fleet. We have a really good calibration and trajectory estimation stack. So you can use that to produce accurate camera poses across time, and then run state-of-the-art NeRF models to produce really good 3D reconstruction by differentiably rendering images from the 3D state. The original NeRF paper used a single neural network to represent the full 3D scene. But then there are other works that are more recent, such as planoxels, that use voxel-based representations to do this. We can also extend these to have both voxels, like voxels of tiny MLPs, or other continuous representation to interpolate the probability to produce these differentiably rendered images. There is one problem with running NeRFs on the wild from real-world images, is because there's a ton of image artifacts that we observe in real-world imagery, such as the sun glare here on the left side, or dirt or dust on the windshield can produce really bad artifacts due to diffraction of the light, or a raindrop can further distort light travel to produce really ghosting artifacts. One way to be robust against this is to use higher level descriptors that are somewhat invariant to the local lighting artifacts, such as glare. Because RGB can be extremely noisy, but adding descriptors on top of RGB can give a layer of semantic protection against changing RGB values. So our goal then is to use this kind of supervision for occupancy networks. And if you think about it, we can take on this differentiable rendering architecture of NeRFs and then stick it as a loss function at the output of these occupancy networks. Since these occupancy networks need to produce the occupancy in few shots, we cannot run the full NeRF optimization in the car, but we can have a reduced optimization that's running in the car all the time in the background, making sure that the occupancy that it produces is explaining all the sensor observations that the car receives at runtime. In addition, this can also be stacked on top at training time to produce good supervision for these networks. So instead of directly supervising the occupancy, which we also do, in addition to that, we can also supervise by just differentiably rendering different sensor data of held out images, for example. This supervision can supervise both the occupancy and also occupancy flow by having some kind of temporal constraints of motion. So that's everything.